Hi guys. Sorry I'm not on campus today. I'm home with a pretty bad migraine, but I did want to get through the rest of our notes on section 7.1 so that you could do the additional practice and complete your Delta Math for the week. So yesterday we talked about verifying trigonometric identities. Today we're going to talk about simplifying and rewriting trigonometric expressions using both what we know about trig and what we know about algebra. This can be useful in lots of situations. As a physicist and mathematician, I used this a lot when I was trying to integrate expressions or do math with expressions. And when you are deriving the expressions, you sometimes end up with really ugly expressions involving lots of trig, and those are difficult to integrate. And so simplifying them down can often make for an easier integration process. I'm sure there are lots of other uses. My brain cannot come up with them right now because I'm in a lot of pain. So bear with me. We're going to practice the important part, which is, oh, I'm in the wrong set. Oh my gosh. We're going to practice the important part, which is using algebra with our trigonometric knowledge, which is sometimes a little bit tricky. I know that you guys know your algebra. Taking that algebra and using it in a new context is sometimes tricky. So let's do a couple examples so you can see what that looks like, and then you have some extra practice built into the note packet. So this first example, it says we can use what we know about factoring to factor the trig expression below. They want us to factor. And I see cos squareds and cos. So what I'm going to do is I'm actually going to make a replacement in this equation. I'm going to let the variable x equal cosine theta. So everywhere I see a cosine theta, I'm going to replace it with an x. And if I do that, I get 2, and then I've got a cosine theta squared, which would be an x squared, plus a cosine theta, which is just an x, minus 1. And that is a little less scary. We can factor this using our skills from Math 2, so we can trial and error. I'm going to factor by grouping because that's how I learned how to handle situations where A is not 1 when I'm factoring. So to factor by grouping, I'm going to look at A times C. So in this case, we've got 2 times negative 1, which equals negative 2. And I'm going to look at factors of negative 2 that add to B. So now I'm going to play the x game, but it's going to look a little bit different than it did when A was 1. So things that multiply to negative 2 and add to B, B is 1. And I know that that would be positive 2, negative 1, because 2 minus 1 is 1. We take those numbers and we use them to split up our middle term into 2 pieces, 2x minus 1x. When we do this, you always want to put the bigger absolute value first. So 2x is going to come before minus 1x. Even if the signs were reversed, this one would still come first because the absolute value 2 is bigger than the absolute value 1. So let's split up that middle term. First term comes along for the ride. Last term comes along for the ride. Middle term splits into 2 pieces that are equivalent. Plus 2x minus 1x. And if I combine those together, I get back to where I started. Next comes the factor by grouping part. I'm going to group the first 2 together. I'm going to group the second terms together, and I'm going to look for what they have in common. In the first pairing, they're both divisible by 2x. In the second pairing, they're both divisible by -1. I'm going to factor that out in front. I'm going to do that division. So I'm going to pull the 2x in front, and I'm going to divide 2x squared by 2x, which just leaves me with an x. And then plus, and 2x divided by 2x is 1. For the second pairing, if I pull out a -1, I'm left with x plus 1. And the check that we did this right is the binomial in both terms excuse me, should be the same binomial. And it is here. That's a good sign. I'm going to divide both terms by x plus 1. I'm going to factor that x plus 1 out in front. So I pull the x plus 1 out in front, and what I'm left with is I'm left with a 2x from the first term, and then I'm left with a -1 from the second term. So 2x squared plus x minus 1 factors into x plus 1, 2x minus 1. And now I'm going to go backwards. I'm going to undo that substitution. So I know x is actually cosine theta. So this expression is cosine theta plus 1 times 2 cos theta minus 1. This x got replaced with cos theta. This x got replaced with cos theta because way back at the beginning, that's how we defined x. X is the same as cosine theta. So those two expressions are equivalent. In this instance, that would be helpful if I were trying to solve the equation 2 cosine squared theta plus cos theta minus 1 is equal to 0. If I wanted to find where those zeros or x-intercepts were. This form would be difficult. This form would be easier because I know when I have two things multiplied together, either the first thing is 0 or the second thing being 0 would make the whole expression 0. And those two binomials are easier to solve separately than this trinomial is all at once. Okay, we're going to try a couple more rapid fire, and then I'm going to set you loose for the additional practice. So the next one says 4 cos squared theta minus 1 says rewrite. So if I do that same replacement, cosine theta becomes x, that's 4x squared minus 1. And I know that that's a difference in squares. A squared minus b squared is just a minus b times a plus b. So I'm pretty sure this is going to factor into 2x minus 1 times 2x plus 1. And if I do that replacement, x is cosine theta, that's going to give me 2 cos theta minus 1 times 2 cos theta plus 1. Yay. I'm starting to recognize that pattern. I probably don't need to do the replacement with x. This next one is also a difference in squares. 25 is squared, 9 is 3 squared, sine squared is sine squared. So this is also that same pattern. Square root of 25 is 5 minus 3 sine theta times 5 plus 3 sine theta. Yay! So those first 3 examples we just did emphasize the fact that those factoring rules that you learned in Math 1, Math 2, Math 3 still work with trig expressions. You can treat sine theta, cos theta, tan theta just like you would x or y. Treat it like a single variable and factor like you would any other expression. All right, last two. We have an expression that says simplify the expression cosecant squared minus cotangent squared using trig identities. So we're going to write the expression off to the side and see if we can do some substitutions and simplifications to make it prettier. And looking at that, without any other context, my instinct is to go back to basic definitions. I know cosecant is 1 over sine, so this is 1 sine squared theta minus, and that second fraction, I know cotangent is cos over sine. And that makes me happy. When denominators match, I can just do math on their numerators. So this is going to be 1 big fraction over sine squared theta. And the numerator is just 1 minus cos squared theta. We've seen that before. We know that off to the side here, cos squared theta plus sine squared theta is equal to 1. If I got sine squared by itself, I would subtract cos from both sides. I would get sine squared theta is 1 minus cos squared theta. So I can do this substitution. I see 1 minus cos squared. I know that's the same as sine squared. So let's do that replacement. On the numerator, we replace 1 cos squared with sine squared. Denominator stays the same. And in a fraction, when the top and bottom are the same, the answer is 1. Much easier to deal with. Yay! Okay, last one. I don't know that you'll see one like this in Delta Math, but you will in the text. And it says simplify the expression below by writing the simplified form in terms of the given trigonometric function. And it gives us 1 minus cos x minus cos x over 1 plus cos x. And they want us to rewrite it in terms of cosecant. So I see a few things with this expression. First, I know cosecant is 1 over sine. And I don't see any sines in my expression. I need to get some sine x in there somehow. The other thing that I spy as an experienced mathematician is I see the first denominator is 1 minus cos. The second denominator is 1 plus cos. And I know that if I multiply those, I get a difference in squares, which would be helpful because 1 minus cos squared is sine squared. We saw that in our last example. We did that replacement here. So if I can get this in the denominator, I can get this in the denominator, which is going to give me a cosecant. So let's go ahead and do that. To do that, I'm going to multiply the first fraction by the second guy's denominator. And I have to do it top and bottom. So I get 1 plus cos x, 1 plus cos x. And then I'm going to multiply the second fraction by the first denominator. So 1 minus cos x, 1 minus cos x. When I do that, first fraction, numerator, 1 times anything is itself, so just 1 plus cos x. Denominator, I have those binomials where the terms are the same except for that sign difference, and I recognize that as difference of squares. 1 minus cos squared x, and then minus. Same thing for the second fraction. Denominator is going to be the same, because I see that same difference in squares pattern. 1 minus cos squared x. And then the numerator, I have 1 minus cos times cos. So I need to distribute that cos to both terms in the binomial. So 1 times cos is cos, minus cos times cos is cos squared. Next step, I know that the denominators are the same, so I can combine the numerators. So 1 big fraction over 1 minus cos squared x, and then I have 1 plus cos x, and then the minus sign here, the subtraction, distributes to everything in the numerator. So minus cos x, and then minus minus becomes plus cos squared x. And then we make two simplifications. I see positive cos x, negative cos x. In the denominator, I see an expression that is equivalent to sine. So this is going to become something over sine squared x, and then the top's going to be 1 plus cos squared x. And then we're going to use that trick to split up the fraction. This is two separate fractions. 1 over sine squared plus cos squared over sine squared. And those two match definitions in our trig library. 1 over sine is cosecant, so this is a cosecant squared. Cos over sine is cotangent, so this is a cotangent squared. So that ugly set of fractions is actually just cosecant squared plus cotangent squared. Yay. All right, you have 4 questions on the very last page of that note packet asking you to do the same thing we were just doing, simplify or verify using the tools that we reviewed, expanding binomials, factoring expressions, substituting in definitions for trig functions, or using trig identities like the Pythagorean identity. When you finish, you've got the rest of the period to work on your Delta Math for week 8. Don't forget, you will have a brief quiz on Monday, so make sure that you understand the notes from this week and that you're comfortable with the Delta Math. If you have any questions, send me an email. Otherwise, I will see you on Monday.